First of all, thank you, Modelon, for hosting this Tech Day on FMI, and I also want to thank Whirlpool and Ford OEMs for being here and presenting. Very much appreciated. Oh, excuse me, I don't want to give a dry talk. Okay. Yeah, I want to take the next 20 minutes to give you an update of where we're at with FMI at MSC and give you some examples, and then tell you a little bit about what we're working on for the coming year. First of all, a couple of minutes just to go over a couple of our products at MSC. We have Adams, which is our 3D multi-body system simulation and modeling environment based on multi-body dynamics, providing real dynamics for functional virtual prototyping and performance improvements of mechanical systems. In Adams, we have different verticals addressing different industry specifications, such as car, chassis, and engine. And these have been developed jointly in collaboration with leading automotive OEMs. A little bit about Adams controls and Adams mechatronics. These are what we call our horizontal plugins to Adams that provide the control system integration. Adams controls is more at the base, and then mechatronics at the vertical level that allow you to deal with hundreds and maybe thousands of variables and different control systems that plug in and that you can update and modify within Adams. Anyway, the purpose of these horizontals is to be able to study the interaction between control and physics-based systems, either electronic, hydraulic, or pneumatic, with the mechanical system, and that's modeled and simulated in Adams. We want to be able to model full nonlinear effects, including flexibility, motion, and collision. And overall provide a better fidelity of the system simulation as a virtual prototype. So currently we integrate seamlessly with control and physics-based systems from Simulink using the S-function method, and then Easyvibe, which is our physics-based 1D solution. I'll talk a little bit more about that in a couple minutes. And then now with we can also integrate seamlessly with other simulation tools using the FMI standard. This in 2012 and we continue in 2013, we're developing a new vertical off of Adams View, which is called Adams Machinery, a very powerful simulation suite for modeling and simulating mechanical drive systems for both the light and heavy industries, machinery industries. So this is essentially a productivity, a suite of productivity gains improvement toolkits that provide easy-to-use wizard type of model creation and provide different levels of fidelity depending how much time you want it to solve for common mechanical parts that you see in machinery. And then we also want to support the parameterization of these mechanical systems, so that allows you to do more what-if studies to optimize the mechanical system. So currently you see the suite of machinery modules in Adams Machinery: gears, belts, chains, bearings, cables, and earlier this year we released an electric motor module, and then we're currently working on a CAM module. In the electric motor module, you can choose to design the electric motor within Adams using curves or functions, motion, or you can also choose to import a electric motor as an FMU or a Simulink S function or Easyvibe library. All right, as far as FMI support in Adams, we first introduced support for FMI in Adams 2013.1, which was released at the beginning of this year, or in Q1. And the support for that was to support both modes for co-simulation. So one can choose to create a slave FMU of your atoms model, and then take that and co-sim in another simulation tool. We support both the visual or batch or invisible mode of FMUs, so that you can either run with atoms visually or in batch. And then we support the master mode, where you can import one or more of your FMUs from other simulation tools as slaves, and then have atoms be the master for the co-simulation. This was implemented using the FMI Library from jmodelica.org. So a plug-in for Modelon for helping and partnering with us to use this library. We found that it worked very well for us and plugged in really reasonably well within the atoms environment. Currently, we support FMI 1.0, and a couple of things to note that we've actually got some feedback on is currently the FMU requirements at runtime are that you do need an atoms installation, and it does require an atoms license to run. We are looking at addressing some of these in the future. So yeah, so if you look at the FMI tools webpage, you'll see atoms there supporting both co-simulation modes, and it's currently marked in yellow. So we have some work to do to validate that interface with other simulation tools. So within atoms is a big, it's a many products within there. So we're using the atoms controls. Atoms controls was a natural way to implement FMU support. So we basically extended that, that interface, atoms controls, to support FMUs. So whether it's exporting or importing, and then also atoms mechatronics, which provides much more rich layer, including signal manager and for your inputs and outputs, and units, better units control, delay functions, all that good stuff on top of atoms controls layer. Again, for atoms mechatronics, we both support the export of your FMU as a plant, or import and generate an external system library within the atoms car database. And then also for atoms chassis, which is, we also support FMU import for atoms chassis. We had a use case to support that. Currently, though, we have not implemented support to create an FMU from an atoms chassis model. We haven't received a requirement for that yet, but for anything that we develop, if there's a request from a customer or a partner to support something, we're always interested in hearing about that. Now, a couple of examples I wanted to show you. First example is something that we had fun with in atoms. So this is an electronic continuously variable transmission example, where we basically use two different atoms products to co-simulation using the FMI interface. So here's an example where we modeled a planetary gear system in atoms machinery, exported that as an FMU, and then imported, and that was a slave FMU, and then we imported that FMU in atoms car, where we modeled the full vehicle, and then hooked that up and done the co-simulation. So here's the schematic of the ECVT and how we hooked it up to get the variable speed of the full vehicle. And so this works, it should work. You can see the plot on the left is the vehicle speed from startup. And then on the right is the actual atoms machinery the planetary gear system working. And the plot on the right shows the angular velocity of the various, the sun, carrier, and ring gears to attain the variable speed. And so this model was taking advantage of regenerative braking and all the good stuff that you would expect from an ECVT implementation. Let's see, did that finish? Yeah. And again, this is an example of just using atoms, the two different modules of atoms, using the FMI, but this planetary gear system could have come from any simulation tool that supported FMU. And likewise, we could have modeled this as well in Atom's chassis instead of Atom's car. Another example I wanted to show you is from an offshore industry. So this is a platform riser example. So here in this example, the Adams model basically includes a riser tensioner system, which is basically 16 cable pulleys systems modeled in Adams machinery, and then the hydraulic cylinders in Simulation X. The motion of the platform is motion controlled in Adams, and then the riser is elastic and is subject to buoyancy and current loads on the system. So here's a close-up view of the platform with the cable systems, and then here's what it actually looks like, in the system. For the Simulation X model, so it's modeled as an FMU. It was a hydraulic model that contains two connecting cylinders in opposite of each other. So that's where you get the 8 FMUs. And then each pair of the opposite cylinders in the Adams model get the force values from the Simulation X model. So in total, we had 8 FMUs imported as slaves and co-simulated with the Adams model, Adams being the master. So here's an example of here's a result of the simulation. So this is a 60-second simulation that took approximately 500 CPU seconds, so not close to real time, 10x real time roughly, but it was solved on but there was nothing to take advantage of a high-performance computing, which is basically solved on a 4-year-old laptop on a single thread. We hope to be able to improve this simulation speed by taking advantage of parallel processing, multi-threading, but we're pretty excited about this. What could happen and this kind of demonstrates the power of the FMU interface within Atoms. And of course, this is an example. 5 minutes, okay. This is an example we're using Simulation X. Could have been an FMU from any simulation tool. There was nothing. It's completely based on the FMI interface. All right, a couple more slides. First of all, what we have on our roadmap is for calendar year 2014. We do plan to support the FMI interface in Easyvibe. We're looking at the co-simulation import and export mode, and in this case, no installation or license requirements to run that FMU in another simulation tool. And then we are looking at supporting model exchange import of FMUs within Atoms. No plans to do export for model exchange. If there's a specific requirement for that, I'd like to hear about that. And then we are looking at adopting the FMI 2.0 interface whenever it's officially released. We have implemented internally using that 2.0 beta 4 version and are ready to release and support 2.0 when it comes out. First of all, I want to take a minute just to mention Easyvibe. So Easyvibe is our block diagram-based tool for physics-based system simulation, and comes with a rich set of application-specific libraries for thermohydraulics, gas dynamics, and multiphase fluid, as well as aerospace vehicle. There are other libraries planned. And then with partnership with Ricardo, we offer automotive-based solutions for for Easyvibe with their libraries. So for Easyvibe, we do plan to support the FMU import into Easyvibe. Here's a mock-up of what it would look like in the Easyvibe interface. So basically, FMU will be an extension in Easyvibe of the extension component. And then when FMU is selected, Easyvibe will unzip the FMU and then parse the description, populate the component data table for that component. And then an export from Easyvibe. So the Easy component will define the interface and specify the variables with inputs and output causalities. And and then, as I mentioned, this will basically use the Easyvibe code generation capability to generate a slave FMU that can be simulated without an Easyvibe installation or license. That's all I have, and thanks again for your attention.